right, thanks, Peter. So for those of you who don't know me, my name is Jeff Clements. I'm a research scientist at DFO in Moncton. I primarily work on shellfish ecology, so I'm not going to talk anything about genetics, about resistance. I'm a buckets and shovels ecologist. I like to go out with my shovel and my bucket and see what's going on with animals in nature. So today I'm going to talk a little bit about what happens when MSX basically kills a bunch of oysters. In terms of the ecosystem, so we all know that oysters filter a lot of water. That affects the ecosystem in various ways. What happens when those oysters get removed? So before I get started, I just want to acknowledge my co-authors and collaborators on these projects. Lots of people from DFO Gulf that have been involved in this project. It's a highly collaborative project with Agriculture Canada as well, Yifeng Zhang's lab, and UPEI as well. So we know that oysters provide many ecosystem benefits, right? Among those are the filtration services that oysters provide. So the often quoted number is that a single oyster can filter up to 50 gallons of water a day and clear debris and particles that are in that water through its feeding. And so they contribute to things like improved water quality, reduced suspension of sediment or turbidity, and they provide a wealth of other ecosystem services as well. But we also know that there are lots of stressors in the ecosystem that can impact oysters in various ways as well. And one that we've become all too familiar with over the last year is disease. So I don't have to talk too much about the diseases that we experience, that our oysters here experience, but we know that with the new and emerging diseases in our region, oyster mortality is a big concern. So a lot of the research that we do in response to that deals with how can we help oysters withstand these sorts of things, but that comes at, I guess, a neglect of understanding what happens to the broader ecosystem and all the other players that are involved in there. And so that's more or less the question that we wanted to ask with this project is, if oysters die, what happens to the ecosystem? Now, when ecosystems are bad, we also try to do other things or other interventions to make those ecosystems better. One example of this is coastal eutrophication, or an increase in the primary productivity in an ecosystem that drives harmful oxygen conditions and bad ecosystem conditions for lots of animals that live within those systems. So to combat eutrophication, our colleague Yifeng has come up with different crop rotation strategies for areas of PEI, where potato farmers can grow crops in different rotations at different times of year to reduce the amount of nutrients that go into our coastal systems and contribute to this eutrophication. Now, when we model these best management practices, we'll call them, that assumes that the background conditions in the aquatic environment stay the same. So if we see that these are effective at combating eutrophication, that automatically assumes that the animals that are already in that ecosystem remain the same. So if these are effective, what happens if any oysters that might live in these systems die off, and do these best management practices, are they still effective at combating that negative condition? So the two questions that we wanted to ask here are, can the mass mortality of oysters from MSX actually affect ecosystem level processes related to this coastal eutrophication problem? And can this influence the efficacy of these management decisions that we make from land? So to do this, we had sort of, a serendipitous sampling program. So in 2021, by happen chance, we did a survey of oysters and a bunch of other bivalves in the Dunk River and the Wheatley River. So the Dunk River we know is in the Bedeck system, very heavily hit by MSX. Now the Wheatley River, we know there's a nice oyster bed there that we can go and sample, but we know that the Wheatley River, at least prior to our sampling in 2025, was completely unaffected by MSX. So we sampled these two systems in 2021 before the disease arrived, and so we had a nice before-after control where we could sample them again after the arrival of the disease and see what happened to the population between that time. Now, when we measure what happened to the population, the other serendipitous thing is that my colleague at DFO, Thomas Guillandet, had what we call an ecosystem model in the system that was heavily impacted by MSX. So this takes various contributions of different contributors within the ecosystem to measure things like phytoplankton biomass or primary productivity, oxygen, these sorts of ecosystem level processes that again relate back to this eutrophication problem. So we can take the oysters out of that system. That model explicitly accounts for the oysters that are in the system. We can take them out of that and measure what happens to the ecosystem. Then we can also apply a model for those agriculture best management practices on top of the model that removes the oysters and see how effective those strategies are at combating eutrophication when oysters are out of the system. So at the end of the day, we end up with these measurements or estimations of the ecosystem based on these quantitative models. When MSX is there, when we engage in those agriculture best management practices, and then when MSX comes in and engages with those best management practices. So first we'll get to the survey data. So in the graph on the left-hand side, you're looking at the change in oyster density between 2021 and 2025 in the Dunk River system. The panel on the right is the Wheatley River system. If it's gray, that's an increase in oyster density that we measured. If it's red, it's a decrease. Now, I should preface this by saying all of the points that we sampled in 2021, we had coordinates for, and so we sampled those exact same points in 2025. So what you can see in the dunk is that every one of the 28 sites that we sampled had a decrease that brought the population basically down to zero. So to put this into context, in 2021 across those 28 sites, we found more than 3,000 oysters. In 2025, we found 5 oysters. In the Wheatley, we see generally the opposite trend. The population actually increased in density from 2021 to 2025. And the big bed there, that's that sort of single line at the top. That's the bed at Oyster Bed Bridge. And again, you can see, it's a pretty dense bed, but it doubled in size between 2021 and 25. So we can just look at that a different way. This is the actual on the top left. You've got the actual change in oyster density. So that's the number of oysters that were lost at each site that we sampled in the dunk. On the bottom, you've got the percent change from 2021 to 2025. So 99.6% reduction in the oyster density at the places that we sampled in the dunk. In the Wheatley, again, you can see that most places had increases. All right, so then basically what we can do is for the dunk system, we can take our model and just take all the oysters out and see what happens to the ecosystem. So that's what we did. We basically took that ecosystem model, took 99.6% of the oysters out, and then we measured things like microalgae concentration. So on the far left, what you're seeing is the net change as a percentage in primary productivity and phytoplankton biomass. And so you can see anywhere from 10 to 20%, depending on where you are in the dunk, you can see a 10 to 20% increase in phytoplankton biomass and primary productivity. We can also look at abiotic environmental conditions. So on the top middle, you're looking at the nitrate N concentration, and then in the bottom middle, you're looking at what happens to dissolved oxygen. So what we can see on the top is that the nitrates are reduced in the system, and the dissolved oxygen goes up. Now, that sounds like it's a good thing, right? The issue in the dunk is that it's already super eutrophic, so the increase in dissolved oxygen actually puts the measurement of oxygen in milligrams per liter too high. So in the dunk, we see oxygen concentrations that are above 10 milligrams per liter, which is not good for animals in that system. We can also look at other ecosystem parameters like macrophytes. On the top right, you're looking at sea lettuce or ulva, and in the bottom, you're looking at eelgrass. So you can see on the top, the removal of oysters from the system doesn't really have any effect on ulva, but we see a net reduction in eelgrass biomass in the system. So basically what we're doing is taking this system, when we remove the oysters, and moving it toward a more eutrophic state, which is not a good thing. So can those land-based agriculture management practices overcome that ecosystem change? That's the next question. And the short answer is no. So here we're looking at microalgae. So again, we're looking at primary productivity and phytoplankton biomass. On the left panels, again, you're looking at the net change in those things for the agriculture best management practices. In the middle, where I'm just reassuring you of the MSX change. And then in the far right, you're looking at the combined effect of the two of them. And what you can see is that the change in primary productivity and phytoplankton biomass associated with the removal of oysters due to MSX completely overrides the small positive effect that those agriculture-based management practices provide. We see an additive effect when we look at nitrates. So on the top, the orange panels there, you're looking at nitrate. So the agriculture best management practice reduces nitrates, and the removal of oysters removes nitrates from the system. So we get this additive sort of positive effect because nitrates in the system are generally considered bad. On the bottom, again, we see this increase in dissolved oxygen due to the removal of oysters, and that overrides any change that the agriculture management practices do, except in the upper arm of the dunk, where the agriculture effect actually overrides the MSX effect. Finally, we can look at those macrophytes, the sea lettuce on the top, and the seagrass or the eelgrass on the bottom. And again, you can see here, MSX had very little effect on the ulva, or the sea lettuce. The agriculture best management practice had a positive effect. It reduced that sea lettuce in the upper reaches of the dunk. And so the combined effect is that positive effect of the agriculture practices. But on the bottom, you can see the agriculture best management practice had a positive effect by increasing eelgrass biomass, but that was completely overridden when you remove the oysters due to MSX. So basically what we saw in the dunk was a drastic decline in that population between 2021 and 2025, 99.6% reduction in oyster density at the sites that we measured. When we throw that into a model, we predict that there's a pretty big ecosystem shift in an already eutrophic system. And so this ecosystem shift due to the loss of oysters completely overrides or negates any positive effect that you might get from land-based management practices. And so if we think about this from an ecosystem management perspective or an environmental management perspective, one thing that managers don't often consider are these acute ecosystem changes that can happen when we have a disease outbreak or perhaps due to climate change. And so we suggest that management really needs to start considering these potential ecosystem changes to make more robust decisions. So thanks for listening. If you have any questions, there's my information, or I can answer them when we get up here. Thanks.